we talked about scatter plots last time, right? And so let's kind of do an overlap at that point first, right? So suppose I have as my x-axis the area of the house. And we'll have that in square feet probably. That's the usual way. In Europe, we do square meters, but it's the same idea. And vertically, we'll have the price of the house. And I won't give you any numbers. I'll just put in some data. And we call this a scatter plot, don't we? Yeah. Now, let's do a quick overlap on things that hopefully we already know how to do, just to make sure that we do. When you look at the scatter plot, isn't there various terms that we can use to describe it, right? Various words that help us to say what we can see. Does anyone want to give me one of the terms I would use for this particular scatter plot?
Linear.
I would agree. Isn't the other choice curvilinear? But that's definitely not a candidate. Okay, give me, there's three main ones. Give me a second thing that we could use, a second term.
Positive.
I think that would be a very good choice. Would we all agree that this is positive? As x gets bigger, so does y? If you want to give it its full title, it's positive association. But I totally agree with you, positive is correct. One more term that we are familiar with. Eric, you got an idea?
Strong?
Oh, I hear
Is it
strong.
strong?
Yes. Eric, were you going to say strong? Good.
Paige also said strong in the chat. I don't know if you saw.
No, I don't get to see chat. I've got too many windows, so chat is not one of my windows. But if you see someone with a question or whatever, please read it out for them. That way I'll be able to get their input if they have a question or if they got an answer. That's good as well. Are we comfortable with the terms and the pictures that are going on, that would be a reasonable way to describe what's going on? Would you also agree that this particular scatter plot does not have any outliers? Would you agree that the data looks pretty compact, right? There's nothing outside the sausage as I describe it, right? We're good. Right. Adding some more terms. The x-axis, right? The horizontal axis, in this case, area of house, is called the explanatory variable. So you're going to see some questions where they're talking about the explanatory variable. When you see the word explanatory variable, think of it as what the x-axis is, right? In this case, area house. And in this case, it's price, and price is called the response variable. You okay with that? It's just another name to add to the many other names we've got. Explanatory variable is essentially the x, response variable is the y. Now, suppose the data was written like this. So there's no scatter plot, and I'll just call it A and B, right? Right, like that. Even although it's written as a table and there is no picture, you should be able to tell which one of those two, the A or the B numbers, which of those is the explanatory variable. When the table is written vertically, what would be the most likely explanatory variable? The A guy or the B guy?
A.
A.
Agreed. And although I can't find one, at least I tried with my other class, can you imagine that sometimes the data is written this way? And if the table was written in the horizontal fashion, again, should we be able to figure out who the explanatory and the response variables are most likely to be? Who would the explanatory variable be in a situation where the table was written this way?
Still A?
Yeah, I should have probably called them P and Q or something. Right. Are we comfortable that the guy on the right is the X, the guy on the left is X, the guy on the right is Y? The guy on top is X, the guy below is Y. And guy is asexual. So Abra, you're a guy. It doesn't mean you're male or female. I use the term guy as a very generic term. So don't send horrible emails to my boss saying I'm sexist and I only ask the males in the class anything. So far, so good. Now, don't know why I moved that because I need it. Can you imagine that you should be able to draw a single straight line that goes through that day? You might even think there's lots of straight lines. Well, I guess technically there is, but there's one straight line that's better than any of the others. And what do we mean by better? I mean, it's closest to the greatest number of dots, right? Can you imagine? You could tweak it, and eventually, if you tried hard enough, you could do it. And it is unique. What that means is, through any scatter plot, there is only one line that's a better fit than any of the others, right? There's one line that's closest to more dots than any of the others, right? And just accept that's a truism. And that line has got a number of names, which I'm now going to write down. You might even come up with some that I've forgotten about. By the way, that's meant to be a single straight line. That bends because I can't draw right. I like that name. It's called the best fitting straight line. I mean, come on, is that not a good name for what it does? Right? It kind of tells you what it is. I like that. Oh, Isabel, what you got for me?
Isn't there a way to calculate on the calculator like an R value that tells you if it's better fitting one way or another?
Yes, and we're going to find that out today.
Oh, okay, sorry.
Oh, no, good point. We're not going to do it on the calculator, although the TI-84 will allow you to do it. We're going to do it on Salt because it's even quicker. Because see, if you do it by calculator, don't you have to type all the numbers in? You can imagine it. I mean, not that you couldn't do it that way, but I think it's much easier if you just hit a Salt button, and I'll show you how to do it on Salt. So this line is called the best fitting. It is also called a regression line. I guess I should put the word line at the end of all these. It's called a regression line. Anybody just heard that term, just didn't know what it was? No? It's a pretty common term that's used. These two guys are the same straight line. They're just two names for the same thing. I just want to try and give you as many different names as I can, so that if you're ever watching a video or in the future you read about something, you say, oh yeah, I know what that is. I wouldn't call it that. I would have called it best fitting line, but I know what you're talking about, right? That kind of thing. They're actually a really weird one. It's called a least squares line. Make my Q look more like a Q. Very strange name, but it's called that. Right, best fitting line, regression line, least squares line. I've forgotten what this one is, but one of my other stats guys says, oh, in Excel, they call it, and now it came back to me. It's called a trend line. Have you ever seen that phrase in Excel spreadsheets where they draw lines through data? Called a trend line. Right, I think I've covered all the good ones. Right, I believe that the textbook's going to use this term. So whenever you see it mentioning regression line, they're talking about this line, okay? But if you see any of these other names, they're still talking about this line. So far, so good? Told you a lot of notes today. Put that over here. Now I'm going to do a side issue. I'm going to return back to Math 94. Just to, Eric, you got a question, or is it light in your face? Okay. We're going to return to some stuff in Math 94 just to get used to it. If I wrote that down in Math 94, what would I be writing the equation of?
Would it be y equals mx plus b?
Yeah, wouldn't it be a straight line? Great. And we're going to, once I finish this, I'm going to return to this and talk about, yeah, this guy here has an equation, just like y equals 3x plus 7. There are two numbers that you can use in the equation of a line. Here they are. If I draw a very basic sketch of what that line might look like, it might look something like this. That number there, the number 7, does anybody remember what name we give to that point on the line where it crosses the y-axis?
The y-intercept.
Y-intercept.
Great, it's called the y-intercept. This number next to the x, this number 3, actually is the slope of the line. Agreed? And the slope of the line would be basically, if you went one along, you know, for every 1 unit along, you'd go 3 up, right? It gives you an idea of how steep the line is. So far, so good. Nothing too weird and wonderful. Would you agree that the equation of the line could be written like that as well, and it wouldn't make one darn bit of difference? Isn't the slope still 3 and the y-intercept still 7? But for some reason, I guess it's statistics people, we like to write our equations like this, where the number goes first and then the multiple of x's goes second. You'll get used to it. You'll see enough of them, okay? Now, suppose I wanted to find an equation for this line. And you just got to imagine that there's a scale here. And the scale is that y-intercept is 50,000, right? I could give you the equation of that line using x's and y's. If I did, it would look something like this. Okay, imagine I got somewhere or other by miracle or whatever, I found the equation of that line and it equals this. Why is that 50,000 here? How can I tell just looking at that picture that that definitely is 50,000? Yeah, Isabel?
Is it's just because it's the y-intercept, right?
Yeah, that's all. So y-intercept. Exactly. And wouldn't you be able to tell that and figure out the slope is 120? Now, normally in statistics, as opposed to normal math, in normal math, that's how we write equations. But in statistics, we tend to write equations more like a formula. So in this case, isn't the y-axis actually the price of the house? And the x is really the area of the house. Would you agree that that is actually an easier formula to get your head around? Because now you've got an idea of what everything is about, right? The predicted price of a house is 50,000 plus 120 area. Are we cool? Now, if I gave you that formula, couldn't I then use it to predict what, a 2,000 square foot house would cost? Well, let's see what that would be. If you tell me that you've got a house and you want to sell it and it's 2,000 square feet, then you should be able to do the predicted price, and it's going to be 50,000 plus 120 times the area. It's 240. And it comes out that you probably will be able to sell that house for 290,000. Are you comfortable about how, if you ask me to find the price of a 2,000 square foot house, this formula is plug and chug and you got your answer? Seem reasonable? Let's put another one in. Suppose I wanted to buy a very small house. So it's only got 1,100 square feet. Then the price would still be 50,000 plus 120 times the 1,100 square feet. So I'd go to my calculator and I'd do 50,000 plus 120 times 1100. And the answer I get is it would still cost me about 182,000 to buy it. Are we comfortable then that I could predict the price of any reasonably sized house using that formula? In whatever area this is, right? You know, if you did Bainbridge Island, things would change, right? Now I'm going to introduce you to another term. Told you a lot of notes today. And we're going to introduce the idea of what's called the residual. I want you to think of the residual as like the error. Because this model is really not an exact size. This is, although I've called it price, actually, you're probably going to see in a lot of textbooks a funny little hat above it. Right, looks like that. And that's because this is to be more realistic. Isn't this the predicted price that that house would sell for? So this house, its predicted price is 290. This little house, its predicted price is 182. But in real life, if I did have a house at this square footage and I sold it, wouldn't it be a miracle if it sold for exactly that? Isn't there a chance it might sell for 295 because there's a little bit of bidding war? Maybe somebody only offers 270 and I'm willing to take the money, right? It will be close to that number, right? It's a prediction, but don't think of it as a, yeah, well, that's it. You got to sell your house for 290 or, you know, it's not right. That's not the way real life works. So the residual is basically going to be the difference between what was predicted and what actually happened. So imagine I add in red what the house really sold for. This house here really sold for 282,000. So somebody made an offer and then you counter offered and you settled at 282, right? Can you imagine that's realistic? That's the kind of thing that really does happen. So we are going to calculate the residual on that particular situation. How would you be able to tell, or what would you do to get the error in this story?
Subtract the actual price from the calculated price.
Okay, and that's it. The residual is, I like your words, I'm going to use it. The actual price, take away the predicted price. Isn't it nice having a little hat? It saves me having to write the word predicted all the time, right? So when you see that little hat, read out loud predicted price, right? Now, in this case, the actual price was 282,000. Predicted price was 290,000. Can you see that it's okay to have a negative number? Wouldn't you, I guess I'll put dollars on that. Wouldn't you probably say that in English, that it sold for 8,000 less than it was predicted? And isn't that 8,000 a measure of the error in the model? In other words, how far out the model was from reality? Don't you want a model where these residuals are really small? Because if these residuals are huge, you probably shouldn't use this formula at all, right? If this formula says it should sell for 290, in reality it sells for 500 or it sells for 100,000, isn't this number totally useless as a predictor of what I should try and sell my house for, right? Wouldn't I try and find some other way of figuring that out? One of the ways that people who do who are in real estate is they do what's called comparables. If you've ever bought a house, and don't they try and find 2, 3, 4 houses very similar in size, same kind of quality build, you know, try and make everything as close to each other. And they can use those 4 houses and say, look, those houses sold for about 280. So how about you starting at 280 yourself and see what goes? So that would be the workaround if you found these residuals are bad. Let's do the small house as another example of that. That one says it should be predicted to be that. But let's say there was a little bit of a price war going on and you actually got 190,000 for it. Right, I could have. Right, you had it in sale for 182, but it sells for 190. So the residual in this case is going to be the actual value, actual price in this case. Take away the predicted price. It sold for 190 and it was predicted to sell for 182. But in this case, isn't the answer a positive number? And that would mean it sold for 8,000 more than it was predicted to sell for. So residuals can be plus, residuals can be negative. Are we good? Now, back to my formula. There's other things you can get from this formula. The predicted price is 50,000 plus 120 times the area of that house. Let's look at what the y-intercept can mean. Sometimes the y-intercept doesn't have any real meaning, right? It's just a number, doesn't really tell you anything. But I think I could do a prediction on this story that the y-intercept does have a meaning in real life. What do you think the $50,000 represents in this model, this formula?
Maybe like the base price.
The base price when what? You're kind of getting there, I think.
I don't know. Paige said starting price in the chat. Just kind of where it starts, because that is where it starts on the y-axis.
That is.
That's where that point begins. So it's
right,
like,
and
it
when
can't
it
be
when
lower than that. I don't know.
that's right. Yeah, you're right. It can't be lower than that. What is the area of a house when the price is 50,000? What's the X value?
0.
And if the X value is 0, the area is 0. Couldn't you interpret that as the cost of the land, right? So if you were buying just a plot of land to build your own house, it would probably cost you 50,000 in this place. So your base price, I would just change that idea a little bit and just say that in this context only, doesn't that probably mean the price of the land when there's no house there? Plot of land. Now,
Yeah,
the
that sounds right.
Good. This fella here, which we know is called the slope, that actually has a meaning as well. And if you're into buying and selling houses, you've probably heard this term before, and you might wondered where it came from. And now I'm about to tell you. What do you think the 120 is all about?
Isn't it like price per square foot?
It is. For every extra square foot of house that you want to buy is going to cost you another $120. So can you imagine if you wanted a house with, say, another extra 100 square feet, do you see it's going to cost you $12,000 more? Does that make sense that if everything else is the same, bigger houses cost you more? How much more? $120 per square foot more, right? So every extra square foot is 120. Now, that number on its own can actually be very often used to get an idea of how expensive places are. So I'm making this up. Let's suppose you're getting a typical house in Bremerton. The answer might be $100 per square foot. Right? That's kind of the going rate. Suppose you want to buy the same kind of house, but it's in Bainbridge Island. Do you think those houses are going to cost you $120 per square foot? I'm making this number up. But would it surprise you that it might be as much as $300 per square foot? Right. If you think Bainbridge Island is bad, can you imagine you went to some place in California? We love watching house programs. Have you ever seen a house program where there's a 1,000 square foot house and it cost $1 million and you think, what? You ever seen that? So in California, in certain places, not everywhere, couldn't it be, I don't know, $580 per square foot? I can do better than that. Suppose you wanted to buy an apartment in central New York, the ones that aren't burnt down, right? The ones that are still there.
Good
If
luck.
yeah, good luck. But what kind of number do you think that would be? It wouldn't surprise me if it was some ridiculous like $2,000 per square foot. Can you see that that slope number is a very good indication of expense? So if you're looking at, buying a house somewhere, and you're just at the start of the process, when you look at houses, somewhere in that detail, won't they tell you price per square foot if you look hard enough? It's a very common number. And so you can say, oh, that's a bit steep. I'm not sure $300 per square foot is worth it. I'd rather get a bigger house in Bremerton than a tiny house in Bainbridge Island. Now, you might have the total opposite opinion. Yeah, I'd rather have a smaller house, but at least it's in Bainbridge Island, so I'm willing to fork out more money, right? And that's a judgment call. But at least, don't you have a number now that you can use to kind of compare them? So slope essentially says, in general, this is what a slope means. For every increase in X, right? So for every increase, every 1 unit in X, the Y value increases or decreases by the slope amount. Okay, let's do it as a general one. Here's two similar equations, and I'm just doing them with X's here. In this one, isn't the slope -20? So for every X, won't the Y go down 1? In this case, for every X, won't the Y go up? Can you see that would be a downwards one and a positive one? So for every increase of 1 in the X, the Y value will increase or decrease by the slope amount. A positive slope means it would increase by that amount. If it's a negative slope, it would decrease by that amount. So in this question, for every 1 square foot, doesn't the price go up by $120? Okay. Do we need another joke yet? Because you've been doing a lot of listening and writing and not really much.
We can always use another joke.
Okay. Has anybody got a good joke for me then? Okay, while you're thinking, should I go? Oh, I'll do my Scottish jokes again. You know how cruel they are. So I've warned you that nobody gets harmed in making of this joke. Scottish husband takes his wife to America on their 50th anniversary. It's a special treat. And they go to the State Fair and they're watching this old-fashioned aircraft, pilot in the front and 2 seats behind, and it takes off and it kind of circles the place. And he looks at it and he says to his wife, "That looks like fun. I think we should do that." And so the aircraft lands and people get out and the pilot gets out and the Scotsman goes over and says, how much does it cost to do that little flight tour that you're doing? And the pilot says, oh, it's $100 each. And the Scotsman says, no, I'm not paying $100. Too much. Scots guy says, make us a deal. What are you willing to take? And so the pilot looks around and there's nobody else. There's nobody waiting to get on. So he's thinking to himself, well, some money's better than nothing. So he says to the Scots guy, okay, you and your wife, I'll make a deal. $100 total. That's it. But if I hear a squeal or a shout or a scream or anything, I want $200, full price. So they shake on it. Pilot gets into the front and the Scotsman gets in behind and his wife gets in behind him and they take off. And they're up in the air and they're doing their little thing that they're meant to do. And the pilot's thinking, I'm not going to stand for this. I want all my money. So instead of doing nice flights, he zooms towards a mountain at the last minute, he zooms off. Nothing. Quiet as anything. So he crashes towards the ground like he's going to crash anyway, and at last minute levels off. Nothing. He does loop-the-loops. He does everything. He flies upside down. He tries everything under the sun. Nothing. So he finally gives up and lands. He gets out and the Scotsman gets out and the pilot goes and says, well, a deal's a deal, and he gets his $100. And the pilot looks at the Scotsman and he said, you know, it must have been really difficult for you to keep quiet. I did everything I could think of to make you scream. And the Scotsman nodded and said, it was really hard. Do you know, I almost screamed when the wife fell out.
Told us that one the first day of school.
Oh, darn it, you should have told me earlier.
I
don't know.
enjoyed hearing it again.
Okay then.
Yeah, we just wanted to hear it again, see if it was going to have a different ending.
No. All right. I'll tell you one I haven't. Have I told you the one about the same Scotsman? Well, a different Scotsman, really, because his wife's dead in that one. Who's a golf fanatic.
We have not heard a golf fanatic one, no.
Okay. So background to this, I don't like golf. I've only got one good eye, so I've virtually no depth perception. So if I try and swing a golf club, I hit soil, I hit air. I very rarely hit the golf ball, so it's not fun for me, so I don't play golf. But lots of people do. And this guy was fanatic. Played every day of the week he could, right? Twice on a Sunday, that kind of guy. And he's out playing golf with his partner, and he's about to take a pot, you know, putt the ball, win the game kind of thing. And at the edge of the golf course, a funeral procession was driving by in the hearse and all the other cars that follow it. And instead of taking his shot, he stops and he takes his cap off and he just waits for all the cars to drive by round the corner out of sight. And then he puts his cap back on and he's about to take his shot. And his pal said, that was really nice of you. I know what kind of fanatical golfer you are. And that's surprising that you did that. That was nice of you. And he turns around to me. He takes his cap back off again and says, yeah, she was a good wife. Are you glad that you waited for that one? Or shouldn't you have just shut up on the first one and let it go? Because it's your own fault you got the second one, not my fault. It's your fault for telling me. No comments about that? Isabel, have you got a comment about that joke?
It kind of sounds like a golfer.
Okay, is that it? That's all again. Okay. Okay, let's return. We are slowly, very, very slowly, coming to the point where we can actually start looking at some homework questions, which I'm assuming you're looking forward to seeing something different. But a couple of other things I want you to kind of get tidied up here. I want you to imagine that you've got your data. Oops. And got a few more dots now that I've figured out where my line's going to go, right? It looks something like that, right? Wouldn't it be nice if there was a number that told us whether or not, well, let's phrase it a better way. If there was a single number that would tell us how good that scatter plot was. In other words, was it a really strong relationship? Was it moderate? Was it weak? You know? And you might think, well, I could just look at it. Well, haven't we had problems when we looked at it? Because apart from, yeah, it's strong or it's weak or it's moderate, don't half the time you want to put moderately strong because it's 50-50. And there's a kind of lots of grey area. Secondly, we haven't spoken about this, but do you know scale can make a difference? Do you know if you do one box is 10 or one box is 100, can't you make the data look really tight or really strong out? Can you imagine just choosing scales? So the problem with just drawing a scatter plot and looking at it and saying that's a strong fit, that's a medium, you know, moderate fit or whatever, is that it's susceptible to the way the scatter plot is drawn. So there is a better way of deciding how good the data is, and it's called the correlation coefficient. And it typically uses the letter R. The correlation coefficient is a number that ranges between -1 and 1. It's a number that is horrendously ugly to calculate by hand, so we never will. We will let SALT calculate it for us. But let me show you what it looks like. If you had a set of data where by sheer luck or whatever, it was a perfect straight line, right? Every single dot was in the same straight line. It has a correlation coefficient of 1. What do you think a perfect everybody on the same straight line would look like in that case?
-1.
Now, if you had some data that had nothing to do with each other, right? The x-axis was the last digit of your telephone number, and the y-axis was how many kids you've got. Can you imagine that would just be a random blob of nothingness, right? There'd be no pattern in it. And a random blob of nothingness would look like somebody shot it with a shotgun, right? A buckshot, right? One of those things, right? What do you think the correlation coefficient is when the data has nothing, no association going on?
0?
It'd be 0. The closer it is to being 1, isn't it the closer to being perfect as a positive line? The closer it is to being -1, the closer it is to being a perfect negative sloped line. And the closer to 0 it is, the closer it is to being nothing at all. So we can set up a kind of rule of thumb. It's not a guaranteed one, different textbooks will change it, but here is the value of R. And here is how we might describe the strength. If the correlation coefficient is being any number between 0.9 to 1, we will say that it's a strong correlation, right? It's a strong fit, right? Very good, very tight, skinny sausage. 0.7 to 0.9, we will call it moderate. (0.1 to 0.7, we'll call that weak. And anything that's less than 0.1, you really should say that there's none. There's nothing going on there. It's just a lot of blobs, dots, randomly done. Now, if we decide, hopefully you do, to stick to this kind of very basic rule of thumb, let's suppose I did some scatter plots, right? And I put them into a computer and I got all the good stuff. But the only thing I tell you are these correlation coefficients. Start with the top one. The correlation coefficient is 0.68. What kind of fit is that?
Weak.
What's 0.005?
None.
Right. What about 0.93?
Strong.
And can we hopefully agree that that one's moderate? Do you know what that takes out? Doesn't that take out the guesstimate? Especially if the scatter plot has a really, can you imagine unscrupulous people choosing a scale to make it look better than it truly was? Right, to make the data look like it's much closer to each other, right? All the dots are pretty close to each other, or vice versa. Do you see how this correlation coefficient doesn't care what the picture looks like? It gives you a number that's totally independent. The analogy to that is, remember when we tried to do outliers with single data points? It was kind of hard sometimes to decide. And then we said, okay, guys, how about the interquartile range test or the plus or minus 3 standard deviation test? Didn't that make life easy? Because then you didn't even need to judge. There was a rule, right? If you were bigger than 3 standard deviations, you're an outlier. I don't care whether my brain says it's 1, it's an outlier, right? Or if you do the interquartile range, there's a test that tells you if you're an outlier in that case. I think everyone prefers certainty in as many situations as they can. Have we now got at least a little certainty as long as we all agree to use this table? So what I want to show you now is how to get the equation, right? The regression line or the line of best fit, how to get this guy and how to get R using SOLVE. So I'm going to nip over. And see if I can find the salt button. There we are. Well, there's one anyway. This
have
one,
Question.
yes.
So when we take our exams, are we
Yes.
going to have access to the SALT then?
Yes, your exams are going to be questions that I will have pulled out of WebAssign and just a bit like a homework that's going to be called test 1.
Got it. But only like one chance instead of 5?
Well, you won't know if you're right or wrong. So I can give you 20 choices.
Got it.
The last one is the one I'm looking at, whether choice 2 is right. If I don't look at that one, right?
Okay.
I only look at the final answer. Plus, I want you to, for those questions you can, to show me working. Now, you won't be able to show me working really for scatter plots, right? And you won't be able to show me working for what equations to use, things like that. But can you do questions like, what's the predicted price of a house? Do you know that one where there was a formula, some numbers and a calculation? So there'll be some questions that you could show me working for. And the reason why I can do them is, even if you got the answer wrong in those questions, if you were doing the process right, you get most of the points. You get partial credit. Right, so right now you're looking at the latitude question. I better shrink this right up. You see it here? Right, so you hit salt button. Oh, shooting spice. No, never mind. You got this fella here, or you will in a minute. Okay, it's transferred. You're going to go to charts and graphs, and you're going to go to scatter plot. And the first variable was latitude, And let's say the second variable was August temperatures. Now, do you see this guy here? That's what my scatter plot would look like, right? So far, so good. If I click on this little box, hey, there's that line I've been talking about. Do you see it now? That's the regression. Now, where are all the numbers I want? Where is the equation of that line that's appeared? And what's the correlation coefficient? You have to scroll down here. Can you see the correlation coefficient is negative 0.7807? You see the correlation coefficient? Negative 0.7807. That's about 0.78. Isn't that kind of, well, in my scale, what would that count as?
Moderate.
It'd be a moderate, right? It's 0.70, 0.9, right? It's a moderate. Now, the equation of the line would be nice if it was written down as an equation, but it's written with these two numbers. So I'm going to write them down on my piece of paper, and then hopefully you can see where I'm getting them from. One of them is the slope and the other is the intercept, right? So in this question, I'm just going to call them y and x's because it's easier for me. The
Can't
slope,
see your paper if you're trying to show it to us. I don't know if you are.
not yet, but I will be.
Okay, cool.
Right, the slope is negative, but thank you for telling me that because a lot of times I forget that and I need to be told it. So the slope is, can I just call that -1? At least take a couple of decimal places it is. Would you agree? Right. And the y-intercept, just to make my life easier, can we just call that 114 if you round it off to nicer numbers? Right. So that line that we have up here has a y-intercept of close to 114, right? You might say, wait a minute, that doesn't look like it's going to go on 114. Well, do you notice that the scale doesn't finish at 0? 0 would be over here. So if the line kept on going, it would be there. And -1's a slope. So let me show you what the equation would look like. You only need two numbers. The predicted y is the y-intercept minus the slope, technically 1x. That would become the predicted temperature. I think this one is temperature in August. Let's check, yeah. So the predicted temperature in August would be 144, take away 1 times the latitude. I wish that number had been 2 or 3 because, you know, it's a bit silly when it's 1, right? But you get the gist of it. Now, suppose there's a city in America, sure there probably is, whose latitude is 30, right? 30 degrees. Then its predicted August temperature will be 144, take away 1 times 30. Its predicted August temperature will be 114 degrees Fahrenheit. Do you see how you can use that formula now to predict any city in America? All you need to do is find out what its latitude is. That makes sense? Did you see how SALT had all the things that we wanted? Now, the correlation coefficient, which you cannot see, is about 0.7807. That we would say is a moderate fit, right? It's not the worst fit in the world. It's not the best fit in the world. It's kind of middle of the road, right? It's moderate. Pretty good, probably usable, right? You could at least play about with it. What does the negative tell me? Why is it, when it says negative 0.7807, what's that telling me?
It's a negative slope.
Yeah, and although the picture's gone, didn't it look like that? So is it the correlation coefficient R? Let's just call it R because that's less words. Isn't R a good indication of the direction of the line, right? Upwards or downwards? And the closer it is to 1 or -1, isn't that a good indication of how good all the data is to fit in that straight line? So there's a lot of information in that guy. Okay. The average temperature in August is 144. Take away 1 times the latitude. Let's see if we can ask some questions about that. The y-intercept is 144 in this case. Right? What would that mean in the context of this story? What would the latitude have to be to get 144?
0.
Right. Now, unless my geography is really bad, isn't 0 the equator? So in the context of this question, doesn't the y-intercept have no real meaning? There isn't any cities in America that are on the equator, right? But if there was one, right, if America was really big and it was in the equator, wouldn't the average temperature be 144, which is not good. Now, the latitude one, right, the slope here does actually have some sense. For every latitude that you increase, right? So if you increase the latitude by 1, won't you decrease the temperature by 1 degree? Wouldn't that be the equivalent of as you go further north, the colder it gets? Right? Latitude, 40 degrees, 41, 42, 43, right? Latitude, right? Bigger number, you're going north. I think the North Pole's, is the North Pole not 90 or 180? I'm trying to remember which it is. I think it's 90. Yeah. So if you went up to the North Pole, allegedly, this model would work. Any questions about anything we've done so far? Because we have covered a lot of stuff.
Will you show us how to do it on the calculators, how to calculate the R value?
I can try. Okay. And I'll stop on this for a minute. I'll go here. In here. Right, so the question is, how do we calculate the R value? Why not the equation of the line while we're at it? Because you probably want to do both at the same time, but it's how you would do it on a TI calculator. So I'm going to hit this little guy here and make him big. Right, are you now looking at a calculator? Okay, so it's a little bit convoluted, so that's why I would rather use Salt, but you might want to do it by hand, and you know, it's helpful to know it. So first thing I'm going to do is I'm going to set up the calculator to do the job, because right now it's not actually going to do it unless I set it up. But you only need to do this piece, the setup piece, once, right? Once that's done, you can leave it and you don't need to worry about it. So down here at 0 in blue, do you see a guy called catalog? Blue button, catalog. And I'm going to go down to a thing called diagnostics on. So if you scroll down this, it's basically, this is where every command that the TI-84 can do is stored. So if you can't find something, you can always find it here. Coming close to it. There, you see the guy that says diagnostic on. You hit enter, and you hit enter again. That's the setup finished, right? It's done. It knows how to do it now. What you now do is you hit start button and you do edit. And in L1, you put the X's, and in L2, you put the Y's. Right. So let's suppose I had some data that I wanted to get the correlation coefficient. I'm just going to make up random numbers right now. I'll do the X's first. Okay, so imagine you got a whole load of X's, and then I scroll over here and I put in what the Y's would be. And again, I'm just randomly picking numbers. So far, so good. So you put your X and your Y values in. That would be that bit done. And where are you hiding? Don't quote me in this. It's been a while since I did it, so I'm kind of looking for it. There we go. Okay, I know where to do it. So hit the start button, go over to Calc, and do you see this guy called linear regression AX plus B? Do you see that guy? Don't do him. I know it's funny, but don't do him. Do you see the guy called linear regression A plus BX? Do you see that one? That's the one you want, because that's the one that's going to be the way this book does it, right? They do the number, then the slope, right? So you hit enter. And what it's looking for now is, where will I get the numbers? And the numbers were stored in L1 and L2. So you go blue button 1, comma, blue button 2. And when I hit enter, everything I need to know, and probably some things I don't want to know, is going to appear. There's my correlation coefficient. You see R is 0.77. Now, A, this number here, the 1.47, is the y-intercept, and B is the slope. So this question would roughly be 1.5 plus 0.7x. And the correlation coefficient is 0.7. Isn't that kind of moderate fit if I plotted that data? Did that help? And if it didn't,
Thank you.
you can always go back and watch this video and pause it and do the next step, pause it and do the next step. So you can kind of break it down into manageable chunks. Any more questions before we actually start looking at the homework questions? We good? Is that a good sign? Oh, good. Because the opposite is, I don't know where to start because there's just too much happening and I can't keep track of all. That's not the one I want. That's the guy we're talking about, this fella. Okay. So we've covered some of these earlier questions, so I'm not going to go through those again. Right. Here is question 5. There's the salt button. One of those 4 pictures is the scar plot I just did. And you can, they don't ask for anything else except that. And here's another set of data, same basic kind of question. Again, they don't ask us for anything that we're interested in. So here we have square footage and the asking price of the house, right? See, this guy and this guy. In this relationship, the explanatory variable X is the asking price and the response variable is the square footage, or is the explanatory variable X the square footage and the response variable is the asking price. So they've gave you 2 choices. This guy is the explanatory variable and this is the response variable. Would you agree that that's the X and that's the Y, so that's the right one? So you would just pick that top. Right. If you hit that guy, can you see that you get a scar plot and you pick the right one? Talks about outliers. We've done that before, so that's new. And here's our first question, which is kind of new for today. Do you see that they've given you the formula that you're going to use? Don't overthink this question. It is as easy as it looks. Estimate the average weight for somebody who's 65 inches tall. Won't you just go here and type in -250 plus 6 lots of 65? And let me tell you right now, the answer is stupid. But that's not your fault and it's not wrong. That's what they told you to do. So I'm going to show you that calculation now, and hopefully you'll agree with me that this answer is stupid. The formula was -250 plus 6 times their height. and they had someone who was 65 inches tall. And this number, by the way, is going to be their average weight, what you would expect a person to weigh at that height. And for a 65-inch tall person, let's see how stupid that answer is. Negative 250 plus 6 times 65, and the answer I get is 140 pounds. I changed my mind. I don't think that's that stupid. Would you agree? 140 is not horribly wrong. It's not great. Yeah, I did it in my head and I got 40. Isn't that why you use calculators instead of doing calculations in your head? Can we pretend a minute that that was 40? Because that's where my brain was going. Wouldn't you agree that that would be a stupid answer? Wouldn't that be an indication that this model is a very weak model? It's not good at telling you the truth. In which case, you probably shouldn't use it to do anything. Right. Okay, that worked out fine. So I just can't count. But you got to remember, this is Friday, and you're the 5th class in a row, plus my officer. And I'm old, and I can't count anyway. So when you put all those things together, it's not a surprise that I can't count, is it? Okay. Question 9 is basically the same question, right? Here's a formula, plug in the numbers and figure out what they are. Now in question, oh, there's a good mistake. You see they've got 2 question A's, so even they make mistakes. Suppose the individual who's 73 inches tall actually weighs that. Calculate the residual. So I think I should do that one. Although you won't see me do it, I will be doing it. So it's negative 250, add 6 times 73. And the answer is 188 pounds. Now, suppose that the individual that they're talking about actually weighed this number. Isn't the residual the actual weight? Take away the predicted weight. In this case, that would be what? The real weight was 7 pounds more than the predicted, right? Remember residual, the real answer. Take away, did I get the right way around? Yeah. Real answer, take away predicted answer. Right, here is a scatter plot. Here is the equation of that scatter plot. Can you imagine answering questions like, what does the slope tell me? Now, the general description of a slope is, for every one, in this case, percentage took, won't the average math score go down by 1.11? Right? So for every 1 increase in the percentage took, the average math will decrease by 1.11. One of those sentences is the same as what I just said. And these 2 guys are use the formula to predict answers, or if somebody gives you an answer, use it to predict the percentage took. Read that over. It's really just to do with words, deterministic. There's that guy again. But this time we got a formula for it. If you give me the formula, I do not like formulas with y's and x's. So if it makes you feel better, won't x be the latitude and y be the August temperature? So if you're looking at this question, will you think of it as predicted August temperature is this number, take away 1.006 times latitude. So x is the latitude, y is the temperature. In which case these questions make a lot more sense. That's a nice way. Isn't that a much better way of writing down the formula? So if I say to you, your hand span is 4 inches, can't you, according to this formula, measure your average height, allegedly, right? I have no evidence to prove this except my gut feeling. I think that is going to be a horrible fit. And the reason I think that is, I don't think it's a very strong connection between the distance between your hands and your height. Can you have tall people with little hands and short people with big hands? And I don't think the two follow each other that much. Abra's looking at her hands to decide what she's got now.
I'm 6 feet tall and I have little hands.
There's a good example of it, right? I think actually I've got pretty little hands and I'm kind of small, so I'm a counter argument to that. But I think, would you agree there's tons of variation? Your hand size probably doesn't have a great relationship to how tall you are. And if that's the case, won't this model probably get you horrible residuals? So that's what my gut feeling would be. Here is a formula to do with pulse rates. It's pretty, pretty much the same old stuff. Another pulse rate question, nothing special. Here's one where that would be predicted January temperature, and that would be latitude. And they're comparing two different places. Do I have enough time for that? Yes, I do. Good. Okay, I'm going to pause on 17 and kind of do it at the side. So in question 17, the predicted temperature, that's what Y represents, the predicted temperature in January is 126, take away 2.34 the latitude. Now you can't see this, but I'm writing it down. Okay, now I'm going to go and do these questions, show you what's expected of you. Okay, so question A says, what is the slope of this line? Okay, what's the slope of this line?
Negative 2.34.
Agreed. If you looked at that, wouldn't the scatter plot look something like that? It'd be going downhill, right? That was pretty good. Interpret the slope in terms of how it affects the January temperature, right? If you increase the latitude by 1, what will happen to the January temperature? If you increase, it'll go down by 2.34. There are 4 sentences there. Pick the one that means the same of what I just said, right? As the latitude increases, the temperature will go down by 2.34. Now, Pittsburgh and Pennsylvania have a latitude of 40, and Boston and Massachusetts had a latitude of 42. Use the slope to predict the difference in expected average temperatures from these two cities. Oh, that's cool. Right. Okay, imagine over here we've got Boston and its latitude is 40, right? And over here we've got Massachusetts, Boston. Oh, I can't read. You've got Pittsburgh and its latitude is 40. And over here you've got Boston and its latitude is 42. And we can use this formula to predict what the difference in temperature is. Well, there's 2 ways to do it. Couldn't I plug 40 and get the answer, 42, get the answer, and then subtract? And if that's the way your brain works, fine. But couldn't I do this? Isn't there 2 degrees of latitude difference between them? And for every 1, don't you get that? So won't 2 of them get you 4.68? Does that make sense how I did it the short way?
Did you just multiply the slope by itself?
I multiplied it by 2.
Oh, okay.
And the reason for 2 is that the difference between these 2 is 2. Can you imagine you found somewhere almost in the Canadian border and another one almost on the Mexican border? Let's pretend I could do that. Let's suppose that was 30 and there's a guy over here and let's say it's 45, right? Then the difference here is at 15 degrees of latitude, doesn't it? But wouldn't that transfer into 2.34 times 15, which is about what, 33 degrees in temperature? So Arizona and Everett, right? There's my 2 extremes. Won't they have a difference of about 33 degrees in winter? So Arizona might get 60 And while they're getting 60, Everett's probably at 31. You know the difference between the two. That would be the marked difference. So if you